In this video, we're going to go through problem 1 on the example problem worksheet for chapter 10. And for this problem, we're just going to go through and solve various types of differential equations that you will encounter in this chapter. Okay? So for the first one, what we have is dy dt is equal to 2t, and we're told that the initial condition, where at t is equal to 0, y is equal to the number 1. Okay? And so what we want to do here is we want to derive an equation that describes y as a function of t. Alright? And so each of these equations for problem 1, they're just going to be of these in a separable form. And so what we need to do, as you may remember from the previous video, for separable differential equations, they all have the form where they're equal to the product of two functions, where the first function is a function of y, and the second one the function of t. So with this differential equation for 1.1, let's identify what part is a function of y and what part is a function of t. And so for this differential equation, on the right-hand side, there really isn't anything that is a function of y. And so what we could say is that our f of y is just 1. Now for the g of t part, we do have something on the right-hand side. We could just say that g of t here is 2t. Alright, and so now that we've identified what our f of y and g of t are, the next step we need to do is we need to move our f of y to the left-hand side and move our d of t to the right-hand side. And so now our differential equation looks like this. So dy over 1 is just dy, and the right-hand side is going to be now 2t times our d of t. Now that we have moved everything to the respective sides, let's now integrate them over their respective variables. So for the left-hand side, our dy, we're going to integrate it with respect to y. And I'm going to do, in this case, a definite integral. Right? And so what that means is I'm going to integrate it between two actual bounds. Right? So I'm going to integrate it from y of 0, which is our initial condition, to y, right, which is the variable we want. Right? And for the right-hand side, I'm going to be integrating our 2t dt. And the bounds I'm going to use, for the lower bound, I'm going to use 0, and for the upper bound, I'm going to use t. And so when we do this definite integral, what we get is y minus y of 0. And on the right-hand side, what we get is 2t squared over 2 minus 2 times 0 squared over 2. Okay? Our y of 0, based on our initial condition, is 1. And this part over here is just 0. And so if we rearrange the equation, and these 2's cancel out, if we rearrange the equation, what we get is just y is equal to t squared plus 1. Alright. So that's a very simple example. Okay? And problem 1.2 is also very similar. So in this video, I'm actually just going to skip it. And what I'm going to do now is I'm going to go to problem 1.3. And in this case, our differential equation looks like this. So dy dt is equal to negative y. And the initial condition we're given, once again, y is equal to 1. Alright. Okay, and so with our differential equation, it seems to have a separable form. And what we could say is that in our separable form, the f of y here is just going to be y. And our g of t is equal to negative 1. Alright, so this is what I'm going to choose for these two functions. If you wanted, you could also just say your f of y is just equal to negative y, and your g of t is equal to 1. That's also fine to do. All right. In any case, I'm going to proceed with these choices. And so what I'll do is I'll move all the y stuff to the left-hand side and all the t stuff to the right-hand side. I'll then do a definite integral of dy over y. And on the right-hand side, it's a definite integral from 0 to t of negative dt. All right. Okay, so for the left-hand side, we're integrating dy over y, and what that gives us is the natural log of y. Okay. And I'll evaluate it at both of its bounds, so we get an ln of y, and in the lower bound, we get an ln of 1. On the right-hand side, when we integrate, what we end up with is, negative t minus a negative 0, I guess. All right. Okay, and now we could simplify. All right, so as we know, the natural log of 1 is just 0, and negative 0 is also 0. Okay. And now that we've simplified, what I want to do is I want to, derive an equation in terms of y is equal to something. And so I'll take the exponential of both sides of what's left over, and what I get is y is equal to the exponential of negative t. Okay. Alright, so also a fairly simple example. Let's move on to 1.4. And what our differential equation now is dy dt is equal to 4 minus y. Okay? And our initial condition, y at t equals 0 is 1. Okay? In this case, the equation is also still separable. And what I'll do is I'll say our f of y, our function of y here, is equal to 4 minus y. And the part that's a function of t, I'll just say is 1. Alright, and so we'll move all the y stuff to the left-hand side, all the t stuff to the right-hand side. And then we'll do a definite integral. So on the left-hand side, I'm integrating basically this function with respect to y. And the right-hand side, I'm going to be integrating just d of t with respect to t. Okay? Alright. Now for the left-hand side, when I integrate it, what I get, and I won't evaluate it immediately, but what I'll get is we still just have a 1 over a function of y, right? And so the integral of that is 4 minus y. But what we have to remember is that the y variable here is multiplied by negative 1. And based on the chain rule, when we integrate, what we also have to remember is that we need to divide by the negative 1 here as well. Okay, so don't forget that when you're integrating. Alright, and I'll just write that this is going to be evaluated from y of 0 to y. And so when we plug that in, what we get is negative ln of 4 minus y, and then we're subtracting the lower bound, so negative ln of 4 minus 1. Right? And on the right hand side, when we integrate, what we get is t minus 0. Okay. Okay, so on the left hand side, this inside part here gives us the natural log of 3, right? Okay, so what I'm going to do is I'm going to just rearrange the equation so that we have it in this form. And then in the end, I want to isolate just y by itself. So what I'll do first is I'll take the exponential of both sides. Exponential of t minus the ln of 3. And based on our log rules, we know that if we have the exponential of, t minus something, that's equivalent to basically the quotient of two exponentials. And we also know that the exponential of a natural log of something just gives us that something, right? The exponential and the natural log just cancel out. Right, and then what I'll do is I'll isolate y, and so what we get in the end is y is equal to 4 minus the exponential of t over 3. Right. So that one's a little bit more complicated, but we still just basically use the same sorts of integrals to solve it. I'll now move on to the last problem, or the last part of problem 1, so 1.5. Right, and so the differential equation we're working with here is our dy dt is now equal, and our initial condition at t is equal to 0, y is equal to 1. Okay? If we treat it as separable, what we could say is that the f of y part is y squared, and the g of t part is just 1. We'll move all the y stuff to the left-hand side, all the t stuff to the right-hand side, and then we'll integrate. So we'll integrate 1 over y squared with respect to y, and the right-hand side, we're just integrating dt. Okay? Alright, and so when we integrate, what we get is 1 over y, but we also have to remember the negative sign here. You could also think of it, rather than 1 over y squared, you could imagine that you're just integrating y to the negative 2, right? And so that might be easier to think in terms of what powers need to be raised and stuff. In any case, 1 over y squared, the integral of that gives you negative 1 over y. And we're going to be evaluating that from y of 0 to y. And so what we get is negative 1 over y minus negative 1 over 1. And that's going to be equal to t minus 0. Okay? And so if we rearrange the equation so that we just isolate the y, what we get is y is equal to 1 over 1 minus t. Okay? And so this format, or this type of differential equation, is one that you'll encounter quite often, especially when you deal with what we call second order reaction kinetics.